Hello, chemistry people. Hope you're all doing well. Keep moving through acids and bases. So this time we left off, we were talking about the definition of acids and bases. And we were first speaking about the Arrhenius definition of an acid and a base. So under the Arrhenius definition, an acid is anything that spits out H plus into solution. So HCl, we get an H and we get the Cl minus. The Cl minus is just the delivery system for the important thing, which is the H plus that makes it an acid. We talked about bases being something where you have a material and it pops out OH in solution. So when it dissociates, we get OH, the OH being our hydroxide ion, being our indicator that it's a base. Right. So naming some of these match the formula with their correct names. All right, this has an H in front of it. So this is an acid and this is a polyatomic ion. So we're going to go with nitrous acid on this one because this is ite. Ite goes to us, nitrous acid. Calcium hydroxide. Here, this is H2SO4. The H in the front letting me know it's an acid. SO4 is sulfate. 8 goes to ick. I ate something icky. So this is sulfuric acid. Here we have H and IO3, which is, we've got iodite. So this is, or iodate. So this is iodic acid. 8 goes to ick. And then down here we've got sodium hydroxide. Right, NaOH, so sodium hydroxide there. So you want to be able to have those named. Now, the thing with the Arrhenius definition of what an acid and a base is it doesn't explain all things that give us acidic properties or basic properties. So we have to expand our definition to the Bronsted-Lowry definition of acids and bases. And in this one, instead of saying an acid is something that puts H plus into solution, in a base is something that puts OH into solution, we want to think about the transfer of a proton. And a proton is just an H plus atom, all right? So you'll hear me say H plus or proton. Those are the same things. Because think about what hydrogen is. Hydrogen is going to be a proton with an electron floating around it, right? Well, if it's a plus, it means we get rid of that electron. What are we left with? We're just left with the proton. So just be comfortable with using H plus or proton interchangeably. So if we're an acid, instead of putting H plus into solution, we're a substance that donates H plus. So we will give up an H plus or a hydrogen. If we're a base, instead of putting OH in solution, we want to classify ourselves as something that accepts H plus. Okay, so an acid donates a proton, a base will accept a proton. So let's look what's happening here. If I take hydrochloric acid and I put it in water, the water is going to steal the hydrogen from the acid and then we'll be left with chlorine. Okay. And so how did I get from water to this H3 plus thing? I had to accept an H plus, right? We went from H2O to H3O. We added a hydrogen. When we add a hydrogen, that makes it a base. Now, what's the other thing here doing? You can probably already guess that it's an acid just by the way it's drawn, but let's look at what's going on. We had HCl and then it changed to Cl. So what did this thing do? It gave up or it donated an H plus, donate an H plus. That means that this thing is behaving as an acid. Those are kind of easy to see because it's HCl, but sometimes they're not that simple. So do know that when we're looking at the Bronsted-Lowry definition of an acid and a base, one thing will be an acid and one thing will be a base. Water is this, it can be what we call amphoteric. It means it can act as either an acid or a base. So you'll see a couple different situations where water is acting as an acid, and sometimes where it's acting as a base. So let's look at a couple other things that go along with Bronsted-Lowry. So here's a great example of a material where if I didn't see these down here, if I was just looking at this ammonia mixing with water, I don't see anything acidic or basic here, right? I don't see an H in the front. I don't see an OH in here. So, what are these things? Well, we got to figure out if it's donating or accepting. I like to pair them up. So find on the reactant side what is similar to the product side. Okay, so these two things are similar to each other. The only thing that differentiates them is the amount of hydrogen. So this has one extra hydrogen. This water looks a lot like this OH. It's just different by, again, one hydrogen. So how do I get from NH3 plus or NH3 to NH4 plus? I accept an H plus, right? So that makes this thing a base. The water in this case is doing what? It had two hydrogens, now it has one hydrogen. So this is donating an H plus. So in this case, the water is acting as the acid. So indirectly, this material ammonia has made OH in solution, right? It didn't break apart to make OH. It stole a hydrogen from the water, and what was left over was the OH. And this is what makes the material, or the final material, basic, right? That OH is what gives us the basic indicator. So you can make OH in solution by either breaking the thing apart and getting OH, or having it steal something from the water to get our OH. But this you wouldn't be able to denote by the Arrhenius definition because we don't see the OH in the original material. So in our Arrhenius definition, we produce H plus. In our Arrhenius definition of a base, we produce OH minus. In the Bronsted-Lowry, we think about a transfer or a donating of H plus or accepting of H plus. Okay, here's some of the other properties. Okay, so looking at these, it says in each of the following equations, identify the Bronsted-Lowry acid and base. So we want to figure out which one of these is of the reactants is acting as the acid and which one is acting as the base. So first one together, find the pairing. So this guy looks very similar to this guy. You good with that? Yeah. This guy looks pretty close to this guy. So figure out what you have to do to become your product. Here, this thing has to donate an H plus. Donate H plus. That means that this is an acid. Once you've figured out the acid, you can automatically go, that's the base, okay? But if we look conceptually what's happening here, it has gained or accepted the H plus. That makes this thing a base. So I want you to do B. Figure out what is behaving as the acid and what is behaving as the base based off of your Bronsted-Lowry. All right, so we find our pairs. So this thing looks like this thing, and then the water Looks like the H3O plus. This is a very similar situation to the above. What is this thing doing? This is donating an H plus. So we call that, anytime you donate an H plus, that's an acid. What's happening here? It's accepting an H plus. So that makes this a base. Now you could sort of use the Arrhenius definition here because like, look at it, it's HF. I mean, that's obviously an acid, but you want to be able to do that. Now these guys over here have a name as well. The reactants that are related, or sorry, the products that are related to the reactants, those have a name and they're conjugate acid bases. So let's move forward there. All right. So we have these conjugate acid base pairs. And what that means is you kind of already have paired them off. You take the two things that look similar to each other that are different by an H, right? One thing will be down in H, one thing will be up in H. In this situation, I call this the acid because there's a hydrogen sitting in the front, and A is just representing anybody for that H plus, okay? That's known as its acid. This thing over here on the other side, its partner, is known as its conjugate base pair. Okay, so this is an acid with a conjugate base pair. This over here, which is our B, is our base. When it adds the hydrogen, it becomes its conjugate acid. So there's an acid to a conjugate base and a base to a conjugate acid. We never put acid to acid or base to base. So again, with this thing, if I know that this is an acid, well, then I know this is a base. If I know this is an acid, I know that's its conjugate base. If I know this is the base, this is its conjugate acid. So you really only have to find one of them and the other four fall into place. But the important thing is that what you'll notice is that when you have your acid, when you lose the hydrogen, you get an overall negative charge because you've lost a proton, right? When you're a base and you gain the hydrogen or you gain that proton, what happens to your charge? You become plus. So we've got sort of neutral charges over here. We want to subtract a charge when we're going to our conjugate base. We want to add a charge when we're going to our conjugate acid. So again, here we go. We've got our acid to our conjugate base, and you can work backwards. So I could take this equation and I could flip it around. And if I flip it around, then this is the base, this is the acid, this base has a conjugate acid, and this acid has a conjugate base. So they all kind of fit together like a puzzle piece. So if we look at the ammonia situation here, what happened? We had NH3. This was the base. We created its conjugate acid over here. And what happened to the charge? We added a hydrogen and our charge went up. Here we have an acid, which is the water. And over here we have its conjugate base. Look at what happened to the charge. It had a neutral charge. We drop a hydrogen and we drop our charge down by 1. Remember, H plus is packing a +1 charge. So I want you to write, well, we'll do one together. So this says, write the conjugate base for each of the following acids. So if this is an acid and I want to write its conjugate base, that means I have to give up an H plus. If I give up an H plus, what is going to be left over here? A, Br, and what happens to its charge? Minus, right? We got rid of the proton. So I want you to do it for the other two, only taking one hydrogen away at a time. Over here, when it says write the conjugate acid for each of the following bases, well, what happens when I have a base? That means I'm going to accept an H plus. So I'm going to take an H plus, and what is left over is this thing smooshed together. We get HNO2. So I want you to do B and C for both of those. Tell me what you expect it to look like in the first one where you drop a hydrogen, what you expect in the second one where you add a hydrogen. All right, so this one here, this is known as a diprotic acid. Di being 2, it has 2 hydrogens. Now know though, when you have diprotic acids like this, or there are sometimes even triprotic acids with 3 H's, the H's will come off one at a time. Okay, so for this thing, if I'm going to get rid of one of these hydrogens, so one of the hydrogens pops off, what am I left with? I'm left with a hydrogen and a sulfur, and my charge should be a minus. Here again, we're going to slouch off one hydrogen at a time. So what will be left over is a hydrogen with that carbonate, and the charge will be minus. We drop the charge down by 1. Now in this situation, we're adding an H plus because we're going from a base to its conjugate acid. So I'm going to add another hydrogen. So this becomes NH4. And what do I have to do? I have to bump my charge up. So this is 0. So it becomes a plus. Over here, I'm going to add a hydrogen. That's going to give me 2 hydrogens and an oxygen, and the charge will bump up. This is the same thing as H2O. Good with that? Cool. Jordan, good? Yeah, cool. Awesome. Okay, so there are the conjugate bases, there are the conjugate acids. Looking at these, tell me the sets that are the correct, identify the sets that contain acid bases conjugate pairs. They're correct conjugate acid base pairs. And it could go in either direction. Could be a base with its acid or an acid with its base. Pretty much find the ones that don't look right, which ones are wrong. I'll give you just 30 seconds. It's kind of like those games you played when you were a little kid. It's like one of these things is not like the other, right? So which one isn't following our rules? Okay, this, we've got HNO2, and then we've got NO2 with a minus charge. So to get from here to here, what did we do? We stripped off to a hydrogen, which gave us the negative charge. I like that one. That's a good one. We're going to keep that one. This one here, I've got H2CO3 and then CO3. What happened here? It slouched off 2 hydrogens and dropped the charge by 2. That is not going to work for us, okay? We don't ever strip hydrogens off 2 at a time. This one, we went from HCl to ClO4. Oh, now we have oxygens in there. That, where did those come from? That definitely isn't following the rule. And we don't like that one either. Here I've got a hydrogen with a sulfur, and it's got a minus charge. And now I've got 2 hydrogens. So I added a hydrogen and my charge went up. That looks good. I like that. Here we had 3 hydrogens, and then we went to 4 hydrogens and we increased our charge just like we did in the last one. I like that as well. Okay, so all 3 of those, this would be an acid with its conjugate base. And these 2 here are bases with their conjugate acid. All right, so these guys are adding hydrogen, accepting hydrogen. This guy is donating a hydrogen. So that's a better way in general to identify acids and bases. The Bronsted-Lowry, or rather the Arrhenius definition, it doesn't capture everything that's acidic and basic. So we've sort of already done this, but guide to writing your acid-base pairs. So you'll add an H plus or subtract an H plus. All right, I want you to look at this thing, and I want you to find the acid, the base, and its conjugate acid and conjugate base. Okay, so each one of these components should be given a name. The reactants will be acid base, the products will be conjugates. So write it out, find the guys that look similar, pair them off, ask yourself what they're doing. Okay, so looking at conjugate acid-base pairs, pair off the guys that look like each other. There's an NO3, there's an NO3. This thing and this thing look like each other. So how do I go from here to here? Well, I have to give up or donate an H. So that makes this an acid. Once you've got one, it fills in quickly. Acid, base. If this is an acid, this has to be a base specifically. Oh, come on. Specifically a conjugate base, right? Because it's the conjugate of the acid, so conjugate base. And then if this is, I didn't draw a line there, but if this is the base, then this has to be the conjugate acid. If I was to flip this and go in the other direction, if I had something like this, NO3 minus plus NH4 plus produces HNO3 plus NH3. You can see we just turned this around. This is over here, this is over here. This will no longer be a conjugate acid. This would just be an acid. And this would be a base. And then we would call the things that were acid and base conjugates. Okay, so this would become the conjugate acid, and this would be the conjugate base. And they would still pair off with their same buddies. Any questions on that, on conjugate acid-base pairs? Just look what's happening with the hydrogen. Okay. Moving forward. I can do it. There we go. All right, so we can classify acids as either strong acids and bases or weak acids and bases. And when I say strong acid, I don't mean like, ooh, it's a really high concentration. It's not related to its concentration. It's related to how much it will dissociate. All right, so if we have a weak acid like HF is an example of a weak acid, it only partially dissociates in water, which means that H and F, some of the H's and F's will break apart, and some of the H's and F's will actually still stay together in the molecular form. So here's an example of a strong acid. A strong acid completely dissociates. So if I take hydrochloric acid and I put it in water, every single one of those hydrogens and chlorines will break apart. Now, how do you know that? If you were to look at an equation, do you see how this arrow is pointing in just one direction? That means that this whole thing is forced all the way in this direction. We now have a thing called a weak acid, and a weak acid will only slightly dissociate in water. So in this case, carbonic acid, when we put it in water, some of them will break apart into its conjugate base, but it will actually also recombine to form the original weak acid as well. How can you see that from an equation? You see the double arrow. So the equation is moving forward in dissociating, and then it's also moving back in recombining. Okay, so we're not as effective as our strong acids. So strong acids, here we go. We've got HI. It completely dissociates into the H3O plus. And when you see H3O plus, know that H3O plus is pretty much the same thing as H plus. When I'm talking about those two things, I'm talking about the same thing. How do they differ? This is just attached to this is H plus, this is H plus attached to a water. Okay, so if you see this, that's also commenting on the H plus. Again, here, this is the same thing as talking about the H plus. It's just an H plus stuck to the water. It's the acidic-y thing. So here the material completely dissociates. Every single iodine breaks apart from every single H plus or H3O plus. No recombination, strong acid. here are the strong acids, and then everything else are weak acids. So there's 6 strong acids. You do want to have access to those. Normally I would have you memorize them, but you get to use notes. So just make sure you have your text or something available. So hydroiodidic acid, HI, hydrobromic acid, HBr, perchloric acid, hydrochloric acid, sulfuric acid, and nitric acid. These are all our strong acids. Every one of these 6 will completely dissociate. Lots of bang for your buck. These guys down here, at pretty much everything else besides those 6, are weak acids. Now, some of them are stronger than other ones. So the hydronium ion, the H3O+, this thing is a stronger acid than, say, your NH4, your ammonia. Okay, as we move up this chart, we become stronger. Then obviously here we are just a full dissociation. Here are some examples of what a weak acid would look like. So if I have HF, we'll go back over here. Where's HF? There's HF, hydrofluoric acid. It's under the weak acid. That means that it doesn't completely dissociate. So we have our molecular HF. Some of it will break apart into H3O+ and F-, but some of it will stay in molecular form. Okay, so we get this sort of oscillation back between the molecular and the ionic, or the broken down version. H2CO3 is a weak acid. Most acids are weak acids. There's just those 6 strong ones. All right, so here is a strong acid, hydrochloric acid, and you can see as far as the particles are concerned, every single combination is broken apart, right? HC2H3O2, this is a weak acid. Most of them stay in the molecule form. Just a couple are breaking apart here and there. Same thing is true for bases. Okay, there are strong bases and there are weak bases. Anything that is formed with group 1A or 2A, so that's like lithium, sodium, calcium, magnesium, all those in column 1 and column 2, those are all going to be strong acids. So potassium hydroxide dissociates completely. A lot of cleaning supplies are really strong bases. So as far as identifying these as a strong or weak acid or base, this first one is under those 6, so we would call that a strong acid. This is under, this is not under the 6, it would have to be the 3, so that would be a weak acid. This is from column 1 with hydroxide, strong base. This is one of the strong acids, one of the 6 strong acids. And then this is a weak base. Why? Because it's OH, but it's combined with something outside of column 1 and column 2. You want to be able to identify strong and weak. Yeah, we don't need to go through all that. All right. So it's interesting when we're looking at the weak acids and bases, we have this arrow that goes back and forth. Right? So some of it's moving forward, some of it's moving backwards, and those are happening simultaneously. Both those reactions are happening at the same time. And so we need to talk about this idea of acid-base equilibrium, right? Or this place where the forward motion and the reverse motion hit an equal rate. That's when we've hit our equilibrium. It also happens here we have hemoglobin combining with oxygen in the bloodstream to produce oxyhemoglobin. If we get into a situation where we don't have enough oxygen, this equation will rush in this direction and we lose that oxyhemoglobin, which is what gives us altitude sickness. All right, so getting deeper into equilibrium. So in an equilibrium reaction, we actually will have 2 reactions taking place. We have the forward direction, and then we have the reverse direction. So HF is a weak acid. We can see that we have HF combining with water to form the F- and the H3O+, right? This is the acid dissociating. But we also have a recombination. So we have the, this is just written over here, we have the F- combining with the H3O+ to give us our original acid molecule and then the neutral water. So both of these things are happening simultaneously. Sometimes you'll see them written out like this. Usually though, what you'll see is just the first one, and they'll just put a back arrow there to let you know that they're both happening. So when we hit this place called equilibrium, equilibrium is when there is no further change in the concentration. It doesn't mean that the reactions aren't happening. We still have things moving from molecule to ions, and we still have ions moving to molecules, but the rate at which things are moving forward and the rate at which things are moving backwards are equal to each other. So we won't find a change in concentration of our reactants or our products. And so here we can see concentration versus time. And what you'll notice is at the very beginning of your reaction, you have all reactant and little product. As time moves forward, your reactant amount will drop and your product amount will increase, right? And then at some point we hit, which would be right here, equilibrium. The concentration of the product has become higher. The concentration of the reactant has become lower. It's not zero though, right? They're still equal. There's still concentrations of both, and they're not changing. They're staying consistent, right? They're still swapping, but it's happening at a equal and opposite rate. So some, hello, sorry, I don't know, what did I do there? Hold on 1 second. Okay, so if we want to talk about concepts of equilibrium, so before equilibrium is reached, the concentrations of the reactants and products are not equal to each other, right? You have too much of one, too much of another. Initially, reactants have a rate of reaction blank than the rate of reaction of the products. So initially, the reactants should be faster than the products, right? Because the reactants are moving towards becoming a product. The products aren't created yet to even be moving back to the reactants. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So the things that are going forward are opposite as the things that are going backwards. And then this is important. At equilibrium, the concentrations of the reactants and products do not change, but they're not equal to each other. Right, so that sometimes people get a little confused there. They think, oh, at equilibrium, it means I have the same number of reactants and products. No, it's just the rate that's changing at the same. All right, the rates is at the same at equilibrium. The concentrations won't change at equilibrium. So there's this thing called Le Chatelier's principle, which talks about equilibrium. And, you know, if you're in a system that you have this equilibrium, like my husband and myself and my daughter, we had a really nice equilibrium going on, and then I had another baby, right? So we put a stressor on the situation, and it kind of messed with our equilibrium. So we had to adjust to find a new equilibrium. Well, that's what Le Chatelier's principle is talking about. We're going to put a stress on our situation or our equation that's in equilibrium and see what happens. So there's a couple of rules. When we alter the concentration of a reactant or product, the rate of the forward and the reverse reaction are no longer equal. One of them is dominating. We put this stress, so then things will have to adjust in order to reestablish equilibrium. This is a nice visual. So here's a water tank, and we have tank A and tank B, and they're connected by a bridge. So tank A gets to flow into tank B, and tank B gets to flow into tank A. And this is at equilibrium, so we have this nice level. Well, what happens if I pour a bunch of water into tank A? I'm stressing out tank A. So what tank A wants to do is flush that water into tank B in order to find what's then a new equilibrium. So the concentration has increased, and then we find a new equilibrium. So this is like before we had our baby, we had some stress. Then we had our baby, and then we found a new equilibrium, and we're balanced, but we're more stressed out than we were in the beginning. So higher concentration. So how that relates to chemistry, okay, so if I've got this equation here, HF, which is a weak acid, combining with water, and we get F minus and H3O plus. Now, if it's a weak acid, we know we're going to have that arrow going forward and back. So if I put HF into solution, if I'm dumping a bunch of HF, right, or I'm going to pump this side up here, it's kind of like filling water into this tank. What will happen is it's going to force the equation to move to the right, or we're going to push the equation towards the product side. We put stress on one side, so the other side will have to beef up or compensate for it. So we would say that we are increasing the rate of the forward reaction, or we're moving or shifting towards our products. What if instead of adding HF, all right, we have that tank or the two tanks, and I put a straw in one tank and I slurp up a bunch of the water, or I decrease the level of water here? Well, this is going to need to compensate for that drop. So water is going to rush, or material is going to rush from this direction back in to fill in the void. We're kind of moving towards whatever the void is, or whatever the lower amount is. So if we remove HF, we're going to put a stress on the system that will increase the reverse reaction. Is that making sense as far as how you want them to flow? So if we increase, we move away from it. If we decrease, we're going to move towards it. Let's look at F instead of HF. So what if we have our F over here and I add F? Well, now instead of putting water into tank A, I'm going to fill tank B up, right? So this side is increasing. If this side is increasing, we're going to force our way over here to drop that water level, or to drop the concentration. So we would be increasing our reverse reaction. Any guess on what would happen? You don't have to say it out loud, but what if we decreased our F minus? What if we drop that down? Now this level is higher than this level. We're going to rush in the forward direction. And that's probably the next slide. No, it's not. Okay, so hold on, hypoxia. I'll talk about you in a second. So some of the rules. So if we add a reactant, it's going to increase the forward direction. We're going to move towards the product. If we remove a reactant, we're going to move towards the reactant to compensate. Same thing with products. If we add product, we're going to move away from that product. If we remove product, we need to fill in or move towards that product. So if we look at, again, this is an equilibrium that we have going on in our bloodstream. If we have high levels of O2, then we will shift in which direction? Lots of oxygen here means that we're going to shift in the forward direction. We're going to have a lot of this oxyhemoglobin in our system. That's why we tend to feel good if we're, breathing in a lot of oxygen. The reverse is where we get into trouble. So if we drop our O2 levels, what happens to our oxyhemoglobin? It needs to move back in this direction. So we have a lot of hemoglobin. We don't have a lot of the oxyhemoglobin. The oxyhemoglobin is what our body uses. It doesn't use oxygen directly. It uses the oxyhemoglobin to get oxygen into our cells. So if we have less than, this says about 29%, we start to experience what's known as hypoxia. So we will increase our respiratory rate. Why are we breathing in more? We're trying to get more oxygen to find this equilibrium again. We can get headache. We lose some of our mental acuteness, fatigue, all these sorts of different things. It's all Le Chatelier's principle happening right there. Here's another reaction that happens in the body. A lot of the reactions in our body are equilibrium reactions. We have kind of this very sensitive homeostasis to our body, where if we're not getting enough of this or that, it can throw everything off. So looking at this here, we've got carbonic acid, and it combines with water in our system to give us H3O plus and HCO3 minus. So using Le Chatelier's principle, I want you to tell me if we're going to move in the direction of the products or the reactants in each of these three things. So adjust this equation using these sets, and then tell me product or reactant. I just need a minute for that probably. Okay, so here we said we're going to add H2CO3. So that's this over here. I'm going to increase it. Think about that water level going up. Where are we going to go? Boom. We're going to rush towards the products. What about here? We're removing HCO3. So over here, I'm going to drop that water level down. Think of your tank. Boom. I'm going to rush towards my products to fill it in. Adding H3O plus. So here I'm going to increase. Think of that water level lifting up. We're going to rush down towards the reactant side. Or these will promote forward, and this will promote a reverse rate of reaction. So water naturally dissociates. When you have a container of water, there's a small percentage of the water that will actually self-ionize. It means it kind of sticks to itself, and it produces a certain percent of H3O plus and OH minus. Okay. The amount of H3O plus and the amount of OH minus is equal to each other. When we're equal to each other, that means we have a neutral solution, right? This is our acid thing, this is our base thing. Neither one is winning out. This self-ionization actually has a very specific concentration. There's a certain amount of self-ionization that's happening. Here's another picture of this process. So the ionization of water, and I had stated earlier that water is amphoteric, meaning it can be an acid or a base. So here's one water molecule. Here's another water molecule. You can see they're identical to each other, but this hydrogen is going to move over here. Okay. Or it looks like in this picture, this hydrogen is moving over here because we have 3 here and only 1 here. So the water has reacted or ionized with itself to produce a percentage of this H3O plus, which is our acid, and an OH minus, which is the base thing. The concentration, again, of those two things is equal in the self-ionization of water. So what is that number? Okay, so this reaction here, in pure water, the concentration of the acidic thing and the basic thing, they equal each other, and it is 1.0 times 10 to the negative 7th, capital M. Capital M being our molarity. So small percentage of it is your acidic thing, and your small percentage is your basic thing. This number you want to know. There's another thing we want to talk about, which is the Kw constant. So Kw is going to be equal to the concentration of your acid times the concentration of your base. And it always equals 1.0 times 10 to the negative 14. Now, all these equations are kind of all over the place. I'm going to try and give you guys a diagram that consolidates all this stuff, really the next like 16 slides. Yeah, we're gonna go make a box over here on our notes. Okay, so let's make a box, and in this upper right-hand corner, I want you to write H3O plus, and I want you to put it in brackets. H3O plus, whenever you see something in brackets like this is talking about concentration. So if you want to, you can say concentration of acid. Sometimes you may see this thing, instead of it saying H3O plus, you may see it written like this, H plus. That is the same thing, okay? We're good with either of those. Those are interchangeable to each other. So we've got that in one corner. Over in this corner, I want you to write OH minus and put it in brackets. That is the concentration of your base. Again, brackets letting us know we're talking about concentration. So concentration of base. And if you want, you can put in parentheses a big M, because this is going to be given to you 99% of the time in molarity. In this lower left-hand corner over here, I want you to put the word pH. We haven't quite talked about pH yet, but we will in a second. And then over in this corner, I want you to write POH. So this, you can put an arrow going back and forth here. And we can relate these two things using the KW constant. So KW equals 1.0 times 10 to the negative 14. Oh my gosh. I skipped ahead. Okay. Sorry, I got distracted. Okay. 1.0 times 10 to the negative 14. And this equals, for any solution, it's not just pure water, but any solution, 1.0 times 10 to the negative 14 will equal H3O plus, so the acid concentration times the base concentration. And I do need to put another arrow here. So sorry, there's going to be an arrow going up and down there. It's kind of messy. In fact, I'm going to put this down here. So this thing equals H3O plus times the OH minus. So this is a really nifty equation because, well, I know what this is. Most of the time, I will be given one of these. I'll give you the acidic thing, and I want to know the basic concentration, or I'll give you the basic concentration, and I want to know the acidic concentration. So let's go sneak back into the slides just to use some of their examples. So here they have the equation. Here's KW equals your acidic thing times your basic thing. You can rearrange this equation. Let's say we wanted to solve for this, OH. It would be our KW divided by our H3O plus. Also true, if we wanted to find H3O plus, that would be KW divided by OH. Okay, so those two equations, very, very helpful. Now, if your H3O plus and your OH minus equal each other, if they're both 1.0 times 10 to the negative 7, we would say our solution is neutral because the acidic thing is equaling the basic thing. What if we get ourselves into a situation where our H3O plus is bigger than our OH minus? We have more H3O plus than we have OH minus. Well, the acid is winning the battle. I'm kind of think of that like they're fighting each other. And there's only so much OH to neutralize this much of the acid, and then there's a bunch of acid left over. So we would say this is acidic. The same thing is true if we have a basic solution, right? In this case, we have a lot of OH. The H3O can only battle, roughly that much OH. So then there's all this extra OH. That means we have a basic solution. So here would be a neutral solution. The two quantities are equal to each other. Here we have an acidic. The H3O plus is greater. Here we have a basic. The OH is greater. So let's do one of these. Okay, so they've got OH is 5.0 times 10 to the negative 8. Okay. So given that we have an OH concentration equal to 5.0 times 10 to the negative 8 big M, and they're going to be super tiny numbers. I want to know, what is the H3O concentration? What is this concentration? And is the thing that we're working with acidic, basic, or is it neutral? So go ahead and try and solve for that using that KW equation. Make sure you're using your EE button or using parentheses. Okay, so when looking at that equation, we know Kw, which is a constant, is 1.0 times 10 to the negative 14, and it equals my H3O plus and my OH minus concentration. Those two things times each other. So I can rearrange the equation to get my H3O plus will just equal Kw divided by whatever my OH concentration is. Kw is a constant. It's that 1.0 times 10 to the negative 14. That's what it always will be. The OH value will change depending on the problem. So in this case, it's 5.0 times 10 to the negative 8. So plug this into your calculator. So we'll take our 1 times 10 to the negative 14, and we're going to divide it by... All right, and I am getting 2.0 times 10 to the 1, 2, 3, 4, 5, 6, 7 to the negative 7. Is that what y'all got? Make sure I plug that into my calculator for this one way I can look on the, don't want to tell you something that isn't true. Yes, to negative 7. Okay, so we know what our concentration of H3O plus is. We know what our concentration of OH minus is. So if we want to figure out if it's acidic, basic, or neutral, we have to see which one is winning. Which one do we have more of? Now we're dealing with negative exponents here, okay? So which number is bigger? This is a bigger number because this negative 7 is closer to the 0 than the negative 8 is. Right? Negative values, opposite. So this is our bigger number. So what's bigger? The acid is bigger. So we're going to say this thing is acidic. Let's do another one of these. So given, you have an H3O plus concentration of 8.2 times 10 to the negative 11. Find your OH concentration. And then tell me, is it acidic, basic, or neutral? All right, so in order to isolate OH, I just need to rearrange the equation in the other direction. So Kw divided by H3O plus will give me my OH concentration, right? If I moved this over, it would give me that original equation. So Kw is the same thing every time, 1 times 10 to the negative 14. And a good way to remember this, hint, hint, wink, wink, what's the maximum number on the pH scale? 14, so that's where that number is coming from. We've got 8.2 times 10 to the negative 11. Okay, so we divide these two numbers and I get 1.2 times 10 to the 1, 2, 3, 4, negative 4. So we're good there. Which number is bigger? All right, 10 to the negative 11 is like super, super small. 10 to the negative 4 is small, but this is like really, really small. So this is the bigger number, which means OH wins. OH is our basic thing. So this solution we would say is basic. You guys good with that? How we can use that, how we can go from, I can give you the concentration of the acid and you can tell me the concentration of the base, or I can give you the concentration of the base and you can tell me the concentration of the acid. And now you can even tell me if the solution is acidic or basic, or if it's neutral. If those two concentrations equal each other, it's neutral. If the acid is greater, it's acidic. If the basic is greater, it's basic. Let's look further into the slides. We can fill in some of these other things. Now here it gives us some more examples. You can always go through those on your own. Okay, the pH scale. So the pH scale is used to describe how acidic something is. If you notice within the word pH, you see the letter H. When we're talking about acids, we're talking about H+. So that's what it's saying. All right, it's a relationship to how acidic something is. Here's cranberry juice. It has a pH of 2.9. The smaller the number on your pH scale, the more acidic you are. So it's like 1, 2, 3, very acidic. 12, 13, 14, much lower acidity. So as far as the pH scale is concerned, it tells you how much acid you have. The values usually range from 0 to 14. You can have negative values, but you won't see that very often. So 0 to 14. It's acidic when the value is less than 7. It's neutral when the value is exactly 7. And it's basic when the value is greater than 7. So if you have usually water has a pH of 7. The water that y'all drink in Asheville is probably more basic because they put a lot of chlorine in there. A lot. I can smell it. Acidic, if you add a little lemon juice, that would be a more acidic solution. Values, again, H3O plus, if this is greater than that halfway breaking point, it's acidic. If it's equal to 1 times 10 to the negative 7, that's the even point, that's neutral. And then if it's less than, we would say that it's basic. So how do we measure pH? We can use a pH meter in the lab. You can use pH paper, which will change colors based off of pH. There's a lot of materials out there that, here's some things. This down here at the end, cabbage juice, that's a piece of cabbage. Okay, so they cook cabbage in water and you get this nasty smelling juice. But cabbage is one of these things that contains anthocyanins, which will change depending on the pH of the material it's in combination with. Hydrangeas are another thing that contain anthocyanins. So if you add lye to your soil, it will change the color of your hydrangeas because you shift the pH. This pH paper you may be familiar with, you may have seen that. And then we also have electric pH meters that will pick up how much H+ is in solution. So here's a scale of pH with some everyday objects. So hydrochloric acid is like right up there at the top. Gastric juice, so your stomach juice. Apple juice, tomato juice, coffee is relatively acidic. Water is basic. So if you have an upset stomach or an acidic stomach, Usually you want to take something that's like more basic. Milk of magnesia can help with an upset stomach. Alka-Seltzer, those things are basic to help kind of balance out the acidic quality. So let's identify each of these as acidic, basic, or neutral. HCl, pH of 1.5, that's acidic. Okay. Pancreatic fluid. Pancreatic fluid has an H3O plus concentration of 1.0 times 10 to the negative 8th. So this value here is smaller than that 1.0 times 10 to the negative 7 breaking point. When you see that number getting bigger like that, it's actually getting smaller. So that means we've got a basic thing. Sprite has a pH of 3, that's acidic. pH of 7, that's neutral. OH, so this is talking about its OH concentration, not its acidic concentration or its H plus concentration. If our OH concentration is less than that negative 7, that means we don't have a lot of this. We will have a lot of the acid. So we'd say this is acidic. And H3O plus, you know, this says we have a really small amount of the H plus. It's smaller than that negative 7, which is our breaking point in the middle. So the OH will win out, or we're basic. So how do we relate pH to concentration? This is the equation right here. And I'm going to put it in our little box, okay? So pH equals the negative log of the H3O plus concentration. So if I want to go from H3O plus, if I know that and I want to solve for my pH, pH equals the negative log of the H3O plus concentration. That looks horrible. Let me rewrite that, give a little more space. pH equals the negative log of the H3O plus concentration. So if I take the concentration of the acid and I take the negative log of it, it's going to pop out my pH. Let's try one. So you definitely need a calculator that has log. I don't want you doing logs in your head. No logs in your head. So let's say that we're given an H3O plus concentration of 1.8 times 10 to the negative 4. I want you to find the pH. I'm going to write the equation. From that last thing that we talked about, pH equals the negative log of the H3O plus concentration. Let me know if you're having trouble finding log on your calculator. And we're not using natural log, so no LNs. It needs to be LOG. Some calculators, you have to plug the concentration in first and then hit the log. Some you write the word log, or you plug the log in and then you put the number in after. I think with my cell phone calculator, I have to put the number in and then I hit the log button. All right, so when I take the log of this concentration, I get negative 3.74, but there's a negative in front of there, right? So we're going to flip that sign. So the pH should be 3.74. Think about your pH scale. Is this acidic? Is this basic? Or is this neutral? This would be acidic. Okay, sort of may seem like a silly question, but as far as math calculations are concerned, what's the opposite of addition? Dun, 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 subtraction, right? What's the opposite of multiplication? Division. What is the opposite of log? 10 to the, okay? So when we have an exponent, 10 to the third power, that to get rid of that, we would log it. So if I've got this equation of pH equals the negative log of H3O plus, and this is just for my people who kind of like math, otherwise you can memorize it. But if I want to get rid of, or if I want to isolate for the H3O plus, I need to get rid of log. So I'm going to take, excuse me, I've got a negative here. So I'm going to move the negative to the other side. So I'm going to get rid of the negative and I'm going to put it on the other side. So negative pH equals the log of H3O plus. If I want to get rid of log, I do 10 to the on both sides. That will cancel this out. So 10 to the negative pH equals my H3O plus concentration. So if I was to give you pH and wanted the concentration of the acid, you could work backwards. So let's add that to our square. And that'll be the last thing we talk about today. So we have an arrow going down, but let's put an arrow going up. If I know pH and I want to calculate for H3O plus, well, H3O plus concentration, the acid concentration, is equal to 10 to the negative pH. Your test is scheduled for this Sunday. I am moving that a week back, all right? So no stress about having to take a test this Sunday. I'll change that either later on today or tomorrow on Moodle. We have a little bit more we still have to do with this chapter, so I didn't want to stress us out. We will complete the box here next time, so make sure you save this. All right, we'll do some practice going in this direction as well. And that will be it for today. Everybody.